Hello everyone, and welcome to this new session in which we're going to implement the Cutmix Data Augmentation strategy with TensorFlow tool. The Cutmix Data Augmentation strategy, though based on the fact that we are combining two different samples, is different from that of the mix-up. Instead, with the Cutmix Data Augmentation, we are going to take at random a patch from one of the samples and attach to the other sample while modifying the labels accordingly. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. We've looked at how to implement data augmentation with TensorFlow and also how to implement more advanced data augmentation strategies like the mix-up. In this section, we'll look at this Cutmix data augmentation strategy. Here, if we suppose that we have these two images, image 1 and image 2, we are going to randomly crop a part of this image. So just like you can see in this output here, they randomly cropped this section from this image and then attach that to this other image such that what you have in the output is this one with this patch. So this is how this Cutmix data augmentation is implemented. If we take this example where we have this cat and this dog right here, we'll try to randomly crop a part from this dog and then attach that part at the same position on this cat image here. To do this cropping operation, we get to TensorFlow image. Let's have this. We have this TensorFlow image and then we have the crop to bounding box. So we click on this and then we have this definition. We see the arguments, we pass in the image, and then we are going to see, or we're going to specify the offset height, offset width, target height, and target width. Now let's explain what all this means. If you have an image like this one, just as is given here, the offset height is a vertical coordinate of the top left corner of the bounding box in the image. And so this means that if we randomly select, for example, this box right here, let's suppose we've randomly selected this box, and our offset height will be this distance. That is, our reference is this top left corner, and our offset height will be this distance here, this distance, and our offset width will be this other distance. So that's how we have this offset height and the offset width. And then the target height is the height of the bounding box. So here we have this bounding box's height and target width, the width of the bounding box. So once you provide this, it will be able to automatically crop out this zone from the image. So coming back to the code, we are going to add this other extra subplot. Let's have this other subplot. Let's paste this code first. Could just copy this out. We have this, and then we have the subplot, third position. What we'll be doing here is we're not going to be having this. We're going to have image. Let's call that image 3. And then what we'll be doing here is we'll be making use of this method. So we have this method, and then we'll specify this offset height, offset width, target height, target width. Let's suppose that our offset height is let's say 20. So here we have 20, 20, say 15. So we have 20, 15, and then let's suppose this target height is 100, and here say 98. Okay, so we have this specified, and then we now pass in the image. The image we'll be using here is image 2, this image here, and that will be it. So here we take this off, and then we could simply show this, pass this here, and that's fine. Now we could take this off. Okay, so we have this. We can now plot this out and see what we get. Okay, as you could see, what we obtain here is the correct it's a cropping of this zone. As you could see, you see that we have something around this. We crop out this zone. So actually it takes more of this, so it's something like this. Now we could modify this, like so we could shift the height and the width. So we could actually maintain the height but shift the width so that we could get more of the dog. So let's do just that. We shift the width. Let's say we take 100 too. We run that, and here is what we get. You see that we get the dog's face this time around. And basically this is how we crop out a region from this image. Now once we've done this cropping, we want to create another image which is made of only this crop, while the remaining zones are actually left out. Now to do that, we'll make use of this other method, which is the path to bounding box. So here we have this image path to bounding box. We'll copy it out and you see how it works. So here we have this image path to bounding box. We're gonna create another plot. So let's increase this number of plots. We have 4, and here 4, and here 4, and let's paste this out first. So we have that. Copy this, paste this out, and then create this foot plot. So we have this foot plot, and now what we'll do is just copy this here and paste it out. So here we paste this out, and then let's get back, and then what we pass in as image now is this cropped image. So let's actually copy this. Let's say we have this crop, let's call it a crop, and then we have, let's take this off, we have the crop, paste it out. Okay, so here we have the crop, and now we're gonna take in the crop now. So after, let's look at this. So after we've had an error before, so let's do this so you could see it better. Okay, so actually what we're saying here is we have this padding to be done, and then we're taking this image, and then we want to pad it or like stamp it on another image which contains only 0 pixels. So let's look at that. We have that. We have this pad, we pass in the crop, we have the offset height and width, and then the target height has to be given. So here we're gonna put in the image size, because we want this to be padded on an image with this dimensions. So we have the image size there. Now we could run this and see what we get. We have this error. Let's modify that quickly. Okay, so here we have this taken off, and then we have 20, 100, 100. Okay, so let's run that, and we should have something reasonable. Offset width again. Oh, okay, we should take this off. Okay, so let's look at this, and there we go. As you could see, we have exactly what we expect. You see that we have this somehow the same image, but we've taken out only this crop. So that's what we actually want. We want to be able to take only this crop, and then take this, like this crop, and then add it with this image here. So what we want to do is we want to take this image now and then add it with this image, so that we could be able to create our data augmentation pipeline. Now we could call this image 4. So let's have this as image 4 equal this here. Let's take this off. Image 4, we paste it out, and then once we paste it out, we could now let's also do another subplot. So we keep on doing the subplots. Let's copy this and paste it here. That's fine. We take the crop, as we have we have this image 4 plus our initial image 1. So let's have that, and then we plot it out. Okay, we're getting this plot, but it isn't very clear. So let's increase that figure size. Let's add the figure size here, and that's it. So we run that again, and then let's look at this now clearer. Okay, here's what we get. So as you could see here, we have this patch, like it looks like something is working, but there is a problem, as we have some sort of mixture of this and the initial image. Now this is logical, since when you do this addition for this black region, you just have only the cat, but for this region you still have the path of this cat image. So what we need to do is we need to remove this path such that when you take this and add to this, it just fits in like a puzzle. Then to crop out just this part from this image, we are going to use the same process we've used for this dog image right here. We simply copy out what we had already here. So we had this cropping, could copy this out and paste it out here. We run that and here's what we get. So you see we have this crop again. Now we'll take this crop and then pad to bounding box as we had done here previously. So let's copy this, and then what do we have? We have the 7th, and then we're gonna pass in this crop cat. So we pass in the crop cat and that's it. But we'll print out this image. So let's call this image 5. And here we have image 5. We run that, and this is exactly what we get. Now the aim is for us to be able to take this and subtract, like take this and subtract this image from it, such that we'll be left with the full cat without this portion, this portion right here. So that said, if just here you do image 1 minus this image 5, you would get this answer. So as you could see, you have this whole cat without this portion, and this is exactly what we want. Now that we have this part, we could add it up with what we wanted to add initially here. So we add it up with this image 4. So here we have plus image 4, and we get the response. And there we go. So we've completed this process of cutting out this portion from here and then fit it in on this image 1. We now take off this other part, take this off, and there we go. We now have the crop, the image 4, crop cat, image 5, and then our final image. We copy out this mix up code we had done previously, so we get back to this. You see that now we could easily integrate this since we have image 1 and image 2. We just left with the labels. Let's just copy this out, cut that, and then here we take this off, paste it out. There we go. And we now have the output image. We now modify this variable name such that crop is crop 1. So here we have crop 1 instead of crop, and then here we have crop 2. So everywhere we meet crop cat, we have crop 2. Here we have crop 1, and then this image 2 is maintained. Is from here we have image 2. Then the image 4, we could turn this to pad 1. So let's call this pad 1. Here we have pad 1, but this is actually pad 2 since we're working with the image 2. So let's call this pad 2 and crop 2. We have the crop 2. Then from this we have crop 1, and here image 1. Here we have crop 1, and here we have this image 5. We'll call it pad 1. Then coming right here, image 5. Image 5 is pad 1, and then image 4, pad 2. Okay, so we have that done. Now we could focus on how to get this bounding boxes. So here we just picked this bounding box, but how do we get this bounding box? To get an answer to this question, we are going to make reference to this formulas which were given in the paper. Right here, we are told that our x is drawn from the uniform distribution, which takes parameters 0 and the width. And then ry is drawn from the uniform distribution, which takes parameters 0 and the height. Now, if we consider this image and say this box randomly picked, then our rx is the center, that is this distance from this, that is based on this origin actually. So we have this vertical distance to this center, which is our ry, and then this horizontal distance, which is our rx. So that's how we obtain ry and rx, which we draw from the uniform distribution. Now to obtain rw and rh, we have this formula right here. RW equal W. W is the width of the image. So we have W times the square root of 1 minus lambda. Recall how we obtained lambda with a mix-up data augmentation strategy. So it's exactly the same way we get lambda. So here we have W times square root of 1 minus lambda. Our H equal the height of the image, times square root of 1 minus lambda 2. Now note that when you multiply this 2, that is, if you take RW times RH, you would have what the numerator right here. Let's have this. RW times RH gives you this numerator, and then if you multiply this 2, you would have WH times the square root of 1 minus lambda. So if you multiply this times this, it gives you WH, this times this, square root of 1 minus lambda times the square root of 1 minus lambda. And you have the square root of 1 minus lambda. Okay, so this is equal RW RH. Now we'll see how they obtain this formula. You see here that since you have RW RH, you could divide here by WH and divide here by WH. This goes away and we're left with this. Obviously, if I have the square root of x times the square root of x, then it is equal x, since I'm having the square root of x squared. Now the square cancels with the square root, it gives you x. So in this case, our x is 1 minus lambda, so this is equal 1 minus lambda. And that's how they obtain this relationship right here. Now that said, we have RH. We've taken this off. Let's go one step back. We have RH. Let's take this. We have, RW, and then we have RH. So this is our RW, the width, and then here's our RH, the height. Our height. But recall that what we have to pass into the method which permits us crop out the zone, for example, is actually this point right here, the top left corner of this bounding box. So we are not going to use the center, but instead it's top left corner. Now how do you get the top left corner? To leave from the center to the top left corner, what we need to take into consideration is the fact that we know this width, for example. Now if we know this distance, and we have this distance from this to this point here, we're supposing this is the center, then we could obviously get this distance here. We could get this distance. To obtain this distance, we need to take all this minus just this portion to obtain this portion right here. Now to obtain this portion is easy because we already know the width RW. So all we need to do is divide this by 2. If we divide RW by 2, then we have this distance. And since we already have this distance Rx, then we can obtain the coordinate, the x coordinate for this point right here. Now the next thing to do is to find our h, and we're going to use to find our y, and we're going to use the same method we did to find our x from base in the top left corner. For our y, we know this distance. Now, do we know this distance? Yes, we know this distance because this is half of the total height, since we are found at the center. Now, if we have this distance, then we could find this distance, because this distance plus this distance gives us this distance. And so to get this distance, we need to take this distance minus this distance to obtain this distance. And if we have this distance, then we have the y coordinate of this point right here. Recall that the reason why we're going through all this is simply because the methods offered by TensorFlow consider that the bounding box coordinates are given based on this top left corner right here. So now we define this function box, which takes in the lambda. Takes in lambda, and then what this does is it makes use of this uniform distribution to obtain Rx, Ry, and then makes use of lambda to obtain Rw, Rh. Now getting back to our uniform distribution, we could copy this right here and then put this in our code. Let's keep the function aside. Let's just have this. So here we have our uniform distribution. Recall our low is 0. Let's take this back. Our low is 0 and our high is the width. So we have here im size, and we have that. Okay, so we've defined this, and then we have Rw, or rather Rx. That's Rx. Now we want to have Ry. Let's have it Rx, Ry, and then we could simply copy this out. There we go. We have this. Let's print this out so we see what we get. Print out Rx, for example. There we go. We have Rx. Im size not defined. We restarted the notebook, so let's get back to redefining this im size. We run that again, and this time around everything looks fine. Now we could draw a sample from this distribution. So let's have sample. We draw a single sample and see what we get. You see we have that. We could take this 0th element, and there we go. So now we're able to draw a sample from our distribution. We could do the same for Ry. So here basically we have this, and then what we want to do is to ensure that this coordinates are integers. So we could cast this. We cast that. We have the d type equal int 32. That's fine. Copy this out and paste it here. Okay, so we have that, and then we cast this too. Now we have Rx, Ry. Let's just do the sampling directly. So we've taken this, and then we do the sampling right here. Sample, take a single sample, take 0 element, and that's fine. We do the same here, paste that out, and everything looks okay. So here we could now print out Rx and Ry. Okay, it looks great. We have now a random Rx and Ry. Go run again so you could see the response. Now we have to obtain im size times the square root of 1 minus lambda. So we suppose that we have lambda. We actually going to use the same method we had used previously. So we suppose here we have our lambda, and then right here to obtain Rw we have the im size times tf mat square root of 1 minus lambda. Okay, 1 minus lambda. Okay, that's fine. Now we have our height, RH, same im size, 1 minus lambda. That's okay. So now we have RH, Rw, and RH, Rx, and Ry. What we'll have to do is to modify this Rx. So we will have Rx equal Rx minus the width divided by 2. Now we want to have a whole number, so we have that minus the width divided by 2. But the width is the im size, so we want to have this im size. There we go. Now if you don't get why we're using this, just get back to this image. To obtain this distance, that's to obtain this coordinate, this top left corner, we'll simply take this distance to the center minus the width divided by 2, and we'll do the same for the height. So that's it. Now we're doing that. We have Rx equal Rx minus im size divided by 2. We repeat the same, and then we have it for Y. Now this is actually this width divided by 2, the width of the box, not the width of the whole image. So we're making an error here. Let's get back to this. We're making use of this width actually, not the width of the whole image. So let's get back, and we put this code after this. So because we're gonna be making use of this RH and Rw. Now we have here, this is R W, that's fine. Okay, now here we're gonna make use of RH. So we have the RH, here RY. Okay, so now we have RX and RY. We could now print this again and then also print out RW and RH. We get in this error. We're told that in this computation right here, the RW is meant to be an int, but it was passed as a float. Since after this computation here, we would have that as a float. Now we could always print out RW the type. Let's run that and see what we get. You see we have a float. So we'll modify that and cast it to ensure that we have an int. There we go. We have d type equal, let's just copy this, tf int 32. So we paste this out here and paste it out this way, tf.cast, and that's fine. So now we expect to have the expected response. And there we go. You see we have Rx, we have Ry, we have Rw, and we have Rh. When we run the cell several times, you'll notice that you will have some negative values popping up from time to time. And this actually happens when, for example, we could have our center at this level, but our weight is so large that it doesn't fit in the image, so it goes in a negative direction. And in this kind of situations, or say in this kind of situation, you could have our box going out of the image. And so we have to ensure that each time we create in this box, we limit it to the image. So this box now, let's take this off. This box now will be this one, and this other box right here will be this box. So we redraw this box, but it wouldn't go out of the image. Our aim is to ensure that we take this part off. Okay, so that's it. We are now going to clip these values programmatically by using the clip by value method. So here we have tf clip by value. There we go. We have that. And then once we pass this in, we're going to specify the range. So we're making sure that the values always fall in this range 0 to the im size. So that's fine. Paste that out, and we have this clip by value right here. So that's it for Rx, Ry, and now after running, you should have only values falling in that range. After clipping, what we have is, if we had, say, initially this box right here, we now have this box. So this is what we get after clipping. Of course, we get the coordinates of the top left corner, but the width in this particular case has changed. In another situation, we could have this, for example, if we have this, in this case, the height changes because we no longer have this height, but now this new height. In a situation where we had a box which was like this, for example, here both the height and the width will have to change. And so based on this new modifications, we have to ensure that we actually pass the right width and the right height. And so what we could do is make sure that once we have the center and we subtract the width, or we subtract half of the width and half of the height to obtain this. Recall we had the center, we had x minus the width divided by 2 to obtain the x coordinate of this point, and then y minus the height divided by 2 to obtain the y coordinate of this point. Now what we'll do is we'll obtain this coordinate right here, but while implementing the clip function. And so this means that if we had a box like normally centered in the image like this, and then we have this, we'll obtain this point top left corner, and then we'll obtain this point bottom right corner just by using x plus w divided by 2 and y plus w divided by 2. So this point is has coordinate x plus w divided by 2 and y plus w divided by 2. And that said, after clipping, we'll have just this now. But what's interesting about the method of clipping after getting this is that now we know exactly where this bottom left is found, or rather this bottom right is found. And if we know, if we have this coordinate and we have this coordinate, then we could recalculate the width and the height. To recalculate the width and the height, it suffices to take, for example, for the width, we take this point here, the x-axis, minus this x-axis right here, or minus the x-axis at this point, because this point and this for the x remain constant, whereas for the y-axis, this point and this also remain constant. So that said, all we need to do now is to take this y minus this y to obtain the height, and then this x minus this x to obtain the width. So based on that, we'll recopy this out and paste. So here we have x bottom right, and y bottom right. All we need to do is to change this and add a plus, and here we add a plus. We clip in by value, so we'll always ensure that it's found in the image. Then also now to obtain this final RW, so our RW now is equal our y bottom right minus our ry, and then the RH will be equal our y instead. This is actually x, and here is x because that's h, that's w, sorry. So you have a ybr minus ry. Okay, so now we've modified the way we calculate this based on the fact that the box may be out of the image, and that now it has some modifications to be done on the width and the height. Now the next step we have to take is, if this RW is equal to 0, then we have to make sure that RW becomes 1. And then here we repeat the same process. If RH equals 0, then RH becomes 1. So that's it. Now we have our RX, our Y, our W, and RH. That said, let's now create our box method. We have our box method right here. Let's have that. And this is what we return. So we return in this. But note that here we're taking the height, the offset height, offset width, target height, target width. And so this means that what we have to output in this method right here has to be our Y, our X, and then our H, our W. So there we go. We return that, and normally everything should be fine. So we have this box method defined. We run that. We get in this error. We should pass in our lambda. Let's go down. We have here lambda. Okay, so we've passed in lambda, and that's fine. Now next thing to do is get back to our mix up, and then we, like we did before with this lambda, we actually could get this, we passed in the lambda, so we could take this off from here. So we run this again, and then we'll define this lambda creation just right here. We have lambda. Let's go back. Okay, we have lambda, and then now we have the box. So this box is gonna produce this output we need here. Let's call it our Y in that order in the documentation. RY, RH, RW equal box of lambda. So now we have box of lambda, and then we have this outputs here. Now instead of passing this, we have our Y, our X, our H, and our W. Let's take this off. Those boxes we fixed initially. We have this. Here we have our y and our x. Scroll down, that's our x. Okay, now we repeat the same process here. We just simply copy this out and paste here, paste it out. Then also we have our y, our x again. So here our y, our x. Let's take that off. Okay, so that's what we have now, and the mix up seems to be fine. So we could get back, run this method, and then run our mix up method again. Now, as usual, we're gonna mix up these two data sets. So it suffices to run this, and then for this one, we are gonna, instead of using the mix up, so here we comment this path, and then we have .map and cutmix. So here we have the cutmix method. We run this, and everything should be fine. We get in this error. Let's check on how we call this. Oh, we call this mix up still. This should be cutmix. Cutmix, we run that. Fine. Let's get back to this here and run it again. Okay, that looks fine. Train data set, everything looks fine. Now we'll try to plot out some value so you see clearly what this looks like. Let's create this new code cell down here, paste this out, and we are going to show this image from our training data. And there we go. We could notice this patch. We could run this again, and this time around we even have a bigger patch. So that's it. We've seen how to come up with this data augmentation strategy. But here we yet to do with a label. So I think if we print out this label, let's print out the label here. See, we print out the label, we're just getting all zeros. Anyways, let's go ahead and implement this section for the label. And to do that, if you could recall this formula, you have 1 minus lambda equal this. So this means that lambda is equal 1 minus RW RH divided by WH. And the reason why we need to do this again is simply because the RH, like at this level where we had this RH and RW modifications, all those clippings, we have to ensure that when creating the label, that condition is verified. So let's get back. Let's check on this formula. Lambda equal 1 minus RH RW. So here again we have lambda equal RH times RW or RWRH. Anyway, we have this RWRH then divided by WH. So here we have im size times im size. Okay, now this is 1 minus all this. Then we apply the same formula for the mix up. We have this lambda. Okay, we've got now a lambda. We now pass this. We have level 1 and level 2. Okay, so there we go. We have our cut mix, and then let's get back. Actually, we will have to rerun this, run our cut mix, and then for our training data we would have to rerun again. So we'll have to run these cells again, run this, and then recreate our training data set. We're getting this error, meaning that lambda is of type float 64. We get back to this, and then we do some casting to make this float 32. Okay, that said, we run our cutmix run. We run this. There we go. Here's cutmix. We run this again, and this is fine now. So we have our train data set, and now we'll go ahead and visualize it. We have this double nonce right here, so it's preferable for us to actually rerun this from this point. Okay, so we run that from that point, and then we get back to this, we run this. Well, that's fine. We can run this, and this should be okay now. Okay, that's fine now. We have everything intact. So that's fine. We can now visualize our data. So you can see we have our patch, and then unlike before where we had either 0 or 1, now we have values between 0 and 1 as our labels. So let's now run this model, compiling and training. After the training is completed, we obtain these results. We see here how this accuracy, let's scroll down here, we have this accuracy which doesn't really change much. So it just around this 46, 48, and high is this 50%. So it's around this 45 to 50% range, and the last two doesn't really change much. Now this is due to the fact that the model is getting confused, and the reason why this model gets confused is because if you have, say, this uninfected cell right here and this parasitized cell, it's actually this portion which permits the model know that the cell is parasitized. And so when you come and crop this part right here and then attach it to this cell here at this position, the actual part of this parasitized cell image which makes this parasitized isn't taken into consideration, and so the model gets confused, as now it doesn't really know how to differentiate between an uninfected and a parasitized cell. Again, this Cutmix data augmentation strategy isn't adapted for our model, though it could be applied in many other problems. We thank you for getting right up to this point, and see you next time.